What if AI could fact-check everything you see online or design personalized medicine tailored just for you? That's the kind of future we're diving into today on AI by AI.
Exactly. We're unpacking some seriously cool research. First up, we'll explore a browser extension called Iffy-Or-Not, ION for short, that helps you spot misinformation online. Think of it as your AI sidekick for critical thinking.
Then we're tackling MoK-RAG, a new way for AI to pull information from multiple sources at once. It's like giving AI a super-powered research assistant, especially when it comes to creating realistic 3D environments.
After that, we're getting into the nitty-gritty of optimization with two-set FOSS-GD. Don't worry, we'll break it down. It's all about making machine learning algorithms learn faster and more efficiently.
And if you've ever wondered how AI grades math problems, we've got you covered with StepMathAgent. This AI doesn't just check the answer, it evaluates the entire problem-solving process.
Finally, we're looking at TXAGENT, an AI designed for precision medicine. It's like having an AI doctor that can analyze drug interactions and personalize treatment plans. Plus, we'll explore an AI framework that predicts how nanoparticles behave in the body, paving the way for smarter drug delivery.
So buckle up, because we're about to explore the cutting edge of AI research, from fighting fake news to revolutionizing medicine. Let's dive in. All right, let's dive into this paper, Iffy-Or-Not, Extending the Web to Support the Critical Evaluation of Fallacious Texts. Sounds like a tool to help us spot BS online, right?
Exactly. It's about a browser extension called Iffy-Or-Not, or ION, designed to make us think twice about what we read. It's all about boosting critical thinking to fight misinformation.
So how does ION work its magic? What are the key features?
It's got three main tricks: highlighting, probing, and chatting. First, it scans the page and highlights content that seems fallacious. Then, when you hover over the highlighted text, it gives you the lowdown on why it's considered a fallacy.
Okay, that's the highlighting part. What about probing?
The probe feature suggests different search queries related to the highlighted content. It even gives you summaries from the web to give you more context. You can also punch in your own search terms.
Cool, so it helps you dig deeper. And the chat feature?
That's where it gets interactive. ION throws out questions to challenge the content, and you can respond and vote on other users' responses. It's like a mini debate right there on the page.
So it's like having a critical thinking coach built into your browser. The paper mentions argumentation theory. What's that all about?
Argumentation theory is basically the study of how we make arguments and try to persuade each other. It's about identifying flaws in reasoning and spotting attempts to manipulate us. ION uses this theory to point out those flaws in online text.
Got it. So ION is trying to help us spot those flaws ourselves. Did they test this thing out with real people?
Yep, they did a user study with 18 participants. They found that ION made people more attentive and skeptical of the content they were reading. It also helped them come up with better search queries.
But it wasn't all sunshine and roses, right? What were some of the downsides?
Some people found that ION missed some fallacies or made inaccurate detections. Others felt it didn't quite align with their goals or the way they like to think. There were also concerns about information overload and people becoming too reliant on the extension.
Over-reliance is a big one. You don't want people switching off their brains completely. The paper talks about logical fallacies. Can we get a quick rundown?
Sure. A logical fallacy is basically a flaw in reasoning that makes an argument invalid. There are formal fallacies, which are about the structure of the argument, and informal fallacies, which are about the content.
Give me some examples of the fallacies ION looks for.
Okay? There's ad hominem, which is attacking the person making the argument instead of the argument itself. Then there's appeal to authority, using someone who's not really an expert as evidence. Appeal to popularity is saying something is true just because a lot of people believe it. And appeal to emotion is trying to win an argument by manipulating emotions instead of using logic.
Those are pretty common online, sadly. What's questionable cause?
That's when you assume one thing caused another just because they're related. Like, after I started wearing this lucky hat, my team won every game.
So Ion uses these fallacies to flag potentially iffy content. The paper also mentions design goals. What were they trying to achieve with Ion?
They had four main goals: encourage critical evaluation, avoid making judgments for the user, offer objective information, and reduce cognitive overload. Basically, they wanted to help people think for themselves without being too heavy-handed.
That makes sense. So they used AI to power these features, right? How accurate was the AI at spotting fallacies?
They did a technical evaluation and found that the AI was about 84% accurate in classifying fallacies. They made that accuracy transparent to the users, which is a good move.
Transparency is key. So what did the user study actually involve?
Participants read Reddit threads with and without Ion. They had to identify dubious content and write messages to inform other readers. The researchers measured things like cognitive load and satisfaction.
And what did they find? Did Ion actually reduce cognitive load?
Interestingly, the difference wasn't statistically significant, but participants did interact more with search functions when using Ion. They were initiating more searches and viewing more search results.
So it encouraged them to dig deeper, even if it didn't necessarily feel easier. What about the different features? Which would people like the most?
The probe feature was the most popular, followed by chat, then highlight. People liked the convenience of having search suggestions and web summaries right there on the page.
Did they find that Ion was more helpful for some people than others?
Yeah, it seemed more helpful for people who weren't already super into effortful thinking, and for those with stronger media literacy skills. But it also seemed to help people who lacked knowledge on the topic, by giving them a starting point.
So it could be a good tool for leveling the playing field. But what are those potential backfiring effects they mentioned?
Information overload was a big concern. Too many highlights and questions could be overwhelming. There was also the implied truth effect, where people might assume that anything not highlighted is automatically accurate.
That's a tricky one. And the over-reliance issue?
Exactly. People might start blindly trusting Ion's judgments instead of thinking for themselves. The researchers suggest things like adding a delay before showing the highlights, or letting users contest the AI's classifications.
Those are some smart ideas. So where could Ion go from here? What are the next steps?
They suggest tailoring Ion to different contexts, like news articles or academic papers, where critical thinking is already expected. They also see potential for using it as an educational tool to teach people about logical fallacies and misinformation.
That's a great point. It could be like a fallacy detector training program. What about adding visuals or expanding it to other media like images and videos?
Definitely. Social media is increasingly visual, so a multimodal approach would be key. They also mention the idea of integrating it with writing tools to help people craft more persuasive and less fallacious arguments.
So it could be a tool for both consuming and creating content. Any limitations to the study we should keep in mind?
They only focused on a few common fallacies, and some of those are pretty obvious. The asynchronous chat in the study wasn't ideal, and the Reddit threads they used might not be representative of all online content. Plus, the sample size was relatively small.
Good to keep those in mind. Overall, though, it sounds like Ion has the potential to be a valuable tool for promoting critical thinking online. It's all about helping people become more discerning consumers of information.
Exactly. It's not about replacing human judgment, but about augmenting it and empowering people to make their own informed decisions.
All right, let's dive into this paper on MoK-RAG. It's all about improving how AI generates content by rethinking how it retrieves information. The core idea is that current systems, which use a single source of knowledge, don't really mimic how humans think.
Exactly. We humans pull information from different places depending on what we're doing. This paper introduces MoK-RAG, which stands for Mixture of Knowledge Paths Enhanced Retrieval-Augmented Generation, to address this. It's a multi-source RAG framework.
So instead of one big pile of data, MoK-RAG splits things up. They functionally partition a large language model LLM corpus into distinct sections. This allows the system to retrieve information from multiple specialized knowledge paths.
Think of it like this. Instead of having one giant textbook, you have separate books for different subjects. When you need to answer a question, you can pull information from the most relevant book or books, instead of searching through everything.
And they've applied this to generating 3D simulated environments, calling it MoK-RAG 3D. They partition 3D assets into distinct sections and organize them based on a hierarchical knowledge tree structure.
Okay, so with MoK-RAG 3D, they're not just throwing random 3D models together. They're categorizing them. Chairs go in the furniture section, plants in the decor section, and so on. The hierarchical tree helps organize how these assets relate to each other in a scene.
One of the interesting things they did was pioneer automated evaluation methods for 3D scenes. Usually it's all manual evaluation, which is time-consuming and subjective.
That's a big deal. Automating the evaluation means they can test and refine their system much faster. Plus, it adds a layer of objectivity to the process.
The paper highlights a problem they call reply missing. This is when the RAG system fails to retrieve all the necessary components for a complete response. It's like asking for a recipe and only getting half the ingredients.
Right? And in the context of 3D environments, this could mean missing essential objects, like a bed in a bedroom or a stove in a kitchen. It makes the generated scene incomplete or nonsensical.
To tackle this, MoK-RAG has 3 key components: a splitting module, a constraint module, and a generation module. The splitting module divides the knowledge base into specialized sections.
So the splitting module is like the librarian who organizes the books by genre. It uses a classifier or an LLM-based agent to assign each piece of knowledge to the right category.
Then comes the constraint module. This organizes the retrieved knowledge, deciding what to include and how to structure it. It has an access policy, which determines whether a retrieved piece of knowledge should be accepted or rejected, and a knowledge organization policy, which defines the structural arrangement of the final knowledge representation.
The access policy is like a filter, making sure only relevant information makes it through. And the knowledge organization policy is like an architect, arranging the pieces into a coherent structure.
Finally, the generation module generates the actual response. In MoK-RAG 3D, this is refined into a dedicated layout module to facilitate scene generation.
So, the layout module takes the organized knowledge and turns it into a 3D scene, placing objects in the right positions and orientations. It's like a construction crew building a house based on the architect's plans.
They found that the reply missing problem is pretty common in 3D environment generation. They identified main objects, which are essential for defining a scene, and paired objects, which frequently appear together.
Yeah, missing a main object is like forgetting the main character in a story. And missing paired objects like a pot and a stove makes the scene feel less realistic.
Their experiments showed that a significant percentage of generated environments were missing either main objects or paired objects, highlighting the need for MoK-RAG 3D.
In MoK-RAG 3D, the splitting module divides the 3D object base into 3 sections: main objects, paired objects, and other objects. This helps ensure that the system retrieves all the necessary elements for a complete scene.
The constraint module then filters and refines the retrieved objects and organizes them into a hierarchical tree. This tree structure helps define the relationships between objects in the scene.
And the layout module uses this tree to establish the spatial relationships between objects, considering things like left-right positioning, rotation, distance, and support. It's all about creating a coherent and realistic scene.
They used the Objaverse 1.0 dataset for object selection and evaluated their system on both residential and diverse scenes. They also introduced automated evaluation methods using LLMs as evaluators.
The human evaluations showed a clear preference for MoK-3D over the baseline system, holodeck, in terms of asset selection, layout coherence, and overall preference. And the automated evaluations confirmed these results.
Importantly, they found that MoK-RAG 3D significantly reduced the reply missing rate, meaning fewer scenes were missing essential objects. This demonstrates the effectiveness of their multi-source retrieval approach.
They also used clip score to assess the visual coherence of the generated scenes. and found that MoK-RAG 3D outperformed holodeck and approached the quality of human-designed scenes.
So overall, MoK-RAG and MoK-RAG G3D seem to be a promising approach for improving the quality and completeness of generated content, especially in complex domains like 3D environment creation.
Definitely. By mimicking how humans retrieve information from diverse sources, they're able to create more realistic and coherent results. The automated evaluation methods are also a valuable contribution, making it easier to develop and refine these systems.
All right, let's dive into this paper on fractional order stochastic gradient descent. The title is a mouthful: Effective Dimension-Aware Fractional Order Stochastic Gradient Descent for Convex Optimization Problems.
Sounds complex. So what's the core idea here? What's fractional order about it?
Okay, so think of regular calculus, derivatives, and integrals. Fractional calculus just extends that to non-integer orders. Instead of a first or second derivative, you could have a 0.5th derivative. It's useful because it lets you model systems with memory, where past states influence the present.
Memory in an optimization algorithm. How does that work?
Exactly. In standard stochastic gradient descent (SGD), you update your parameters based only on the current gradient. Fractional order SGD incorporates a partial summation of past gradients. It's like the algorithm remembers where it's been and uses that information to smooth out the updates.
Okay, I see. So it's trying to be smarter by looking at the history of the gradients. What's the benefit?
The potential benefit is better convergence and robustness, especially in dynamic systems or complex landscapes. But there's a catch. The fractional exponent, which controls how much memory you use, is hard to tune. Too little and you don't get the benefit. Too much and you get oscillations or instability.
The classic hyperparameter tuning problem. So what's their solution?
They introduced something called two-said fractional order stochastic gradient descent, or 2-SEFGD. The key is the two-scale effective dimension 2-seed algorithm. It dynamically adjusts the fractional exponent based on the model's sensitivity and effective dimensionality.
Effective dimension? What's that about?
Think of it this way. In a neural network with millions of parameters, not all of them are equally important. Some directions in the parameter space are flat, meaning changes there don't affect the output much. 2-SED tries to figure out which directions are actually sensitive and adjusts the learning accordingly.
So it's like figuring out which knobs on a machine actually do something important.
Precisely. 2-SED uses the Fisher informatrix to measure this local sensitivity. The FIM essentially tells you how much the model's output changes when you tweak a parameter. 2-SED combines this curvature information with the overall number of parameters to get a better sense of the effective dimension.
Okay, I'm following. So how does 2-SED adjust the fractional exponent in FOSS-GD?
If 2-SED detects high curvature, meaning the model is very sensitive in certain directions, it lowers the fractional exponent. This reduces the influence of older gradients and prevents overshooting. Conversely, in flatter regions, it increases the exponent to leverage more memory and accelerate convergence.
That makes sense. It's like a self-adjusting memory knob. What kind of math are they using to make this happen?
They use the Caputo fractional derivative, which is a specific type of fractional derivative that's well suited for handling initial conditions. The update rule involves a weighted sum of past gradients, where the weights are determined by the fractional exponent and a small offset to prevent stalling.
And they have a convergence proof, right?
Yep. They provide a detailed convergence proof under convex objectives, making assumptions about smoothness, bounded gradients, and bounded iterates. They show that their method achieves faster and more stable convergence compared to naive FOSS-GD.
What about the experiments? What kind of problems did they test it on?
They tested it on an autoregressive AR system identification task, both with Gaussian noise and with alpha-stable noise, which is a heavy-tailed distribution that can cause outliers. The 2-SED FOGD consistently outperformed regular FOSGD, especially in the presence of alpha-stable noise.
So it's more robust to outliers.
Exactly. The adaptive fractional exponent helps to mitigate the impact of those extreme values. The results showed that 2 Cephos GD achieved closer estimates to the true parameters with smaller estimation errors.
Interesting. So the key takeaway is that by dynamically adjusting the fractional exponent based on the geometry of the loss landscape, they can get the benefits of fractional order methods without the instability and tuning headaches.
That's the gist of it. It's a clever way to combine fractional calculus with dimension-aware optimization, potentially leading to more robust and efficient training of machine learning models. All right, let's dive into this paper on StepMathAgent. It's all about evaluating how well large language models, or LLMs, handle math problems, and it seems like the current methods aren't cutting it.
Yeah, the abstract mentions that existing evaluations mainly focus on the final answers. That sounds pretty limiting. What's the big deal with just checking the final answer?
Well, think about it. The paper points out 3 major issues. First, it's inaccurate. An LLM could get the right answer by luck, even if its process is totally wrong. Or it could have a correct process but make a small calculation error at the end. Both would be scored the same if you only look at the final answer.
That makes sense. So it's not really reflecting the model's true understanding of the math.
Exactly. Second, some problem types like proofs or open-ended questions don't even have a single correct answer. How do you evaluate those based solely on the final result?
Good point. You'd be missing the whole point of the exercise, which is the reasoning itself.
And third, it's uninterpretable. If the LLM gets the wrong answer, you have no idea where it went wrong. Was it a misunderstanding of the initial conditions, a flaw in the logic, a simple arithmetic mistake? You're left completely in the dark.
Okay, I'm convinced. So what's this StepMathAgent they're proposing?
It's a new approach that evaluates the process of solving math problems, not just the answer. It's based on something called tree of error, which sounds pretty cool.
Tree of error? Sounds like something out of a fantasy novel. What does that even mean in this context?
Basically, it's a way to map out all the possible error chains in a solution. The agent breaks down the solution into logical steps, scores each step, and then figures out how errors in earlier steps might have led to errors later on. It's like tracing the roots of a problem.
So it's not just saying this step is wrong, but also this step is wrong because of what happened earlier.
Precisely. The paper mentions 4 internal core operations that make this happen. First, logical step segmentation, which is breaking down the solution into individual steps. Then, step scoring, where each step is evaluated as correct, incorrect, or correct but meaningless.
Correct but meaningless. That's a new one. What's that about?
It's for steps that are technically correct in isolation, but they're based on a previous mistake, so they don't actually contribute to a valid solution. It's a clever way to track how errors propagate.
Got it. So what are the other 2 internal operations?
Next is score aggregation, which combines the individual step scores into an overall score for the solution. And finally, error tree generation, which is where the tree of error is actually built, showing the relationships between the errors.
Okay, that sounds like a solid foundation. But the paper also mentions external extension modules. What are those for?
Those are designed to make StepMathAgent more adaptable to different situations. There's difficulty calibration, which decides if a problem is simple enough that you don't even need process evaluation. You can just check the answer.
That's smart. No need to over-engineer things for simple problems.
Then there's simplicity evaluation, which penalizes solutions that are overly complicated or include unnecessary steps. Completeness validation does the opposite. It penalizes solutions that skip steps or leave out important information. And finally, format assessment, which checks if the solution follows the required formatting guidelines, like using LaTeX correctly for mathematical notation.
So it's really trying to mimic a human grader who's looking at not just the correctness, but also the clarity, completeness, and presentation of the solution.
Exactly. And to test all this, they created a new benchmark dataset called StepMathBench. It's got 1,000 step-divided process evaluation instances based on 200 high-quality math problems.
That sounds like a lot of work. How did they create that dataset?
They started with 200 problems, carefully chosen to cover different types of math, difficulty levels, and educational levels. Then they used LLMs to generate solutions for each problem. And finally, they had human annotators, all with master's degrees, mind you, segment and score each solution.
Wow, that's a pretty rigorous process. So what were the results? Did StepMathAgent actually perform better than existing methods?
According to the paper, yes! It outperformed all the other methods they compared it to, and it showed a high degree of alignment with human scoring preferences. Plus, the error trees it generated provided valuable insights into where the LLMs were struggling.
That's great. So it's not just about getting a score, but also about understanding why the model got that score.
Precisely. The paper highlights how StepMathAgent can help identify things like minor errors early on that snowball into major problems, or cases where LLMs guess the right answer without actually reasoning correctly.
That's super useful for improving LLM's mathematical abilities. It's like having a detailed diagnostic report instead of just a pass-fail grade.
And they even did an ablation study to see how much each of the external modules contributed to the overall performance. It turns out that each module does what it's supposed to do, but combining them all doesn't always lead to better results. It depends on the specific evaluation scenario.
That makes sense. You wouldn't want to be too strict in every situation. Sometimes you might prioritize completeness over simplicity, or vice versa.
Exactly. The key takeaway is that StepMathAgent offers a more nuanced and interpretable way to evaluate LLM's mathematical skills, which can ultimately lead to better models and a deeper understanding of their reasoning abilities.
So what are the limitations of this study?
Well, the authors themselves acknowledge a few. First, StepMath Bench, while innovative, is still relatively small. Creating more of these process evaluation datasets is crucial. Second, they only explored 4 external modules, and there's room for more, like step length recommendation. And third, they only compared StepMathAgent to a limited number of LLMs due to cost constraints.
Okay, so there's definitely room for future research. But overall, it sounds like StepMathAgent is a significant step forward in how we evaluate LLM's mathematical capabilities.
I agree. It's a move away from just checking the answer and towards understanding the reasoning behind it. And that's essential if we want to build truly intelligent and reliable AI systems. Okay, so we're diving into this paper about TXAGENT, which is an AI agent designed for therapeutic reasoning. It's all about helping doctors make better, more personalized treatment decisions. What's really cool is that it uses a universe of tools, 211 of them to be exact, to analyze drug interactions, contraindications, and tailor treatment strategies to the patient's specific needs.
211 tools. That sounds like a lot. What kind of tools are we talking about here?
Think of it as a super-powered medical toolbox. These tools pull data from trusted sources like the FDA, Open Targets, and the Human Phenotype Ontology. They cover everything from drug mechanisms and interactions to clinical guidelines and disease annotations. Basically, anything a doctor might need to consider when prescribing medication.
So it's like having a constantly updated medical library at your fingertips. But how does TXAGENT actually use these tools to make recommendations?
That's where the multi-step reasoning comes in. TXAGENT doesn't just look up information, it actually thinks through the problem. It starts by identifying the task, then selects the relevant tools, executes them, and synthesizes the information to refine its recommendations. It's an iterative process, meaning it can go back and reevaluate its plan as needed.
Okay, so it's not just spitting out answers. It's showing its work. That sounds way more trustworthy than just relying on a black box AI. But what's wrong with current methods? Why do we need TXAGENT?
Great question. Current large language models, or LLMs, often lack real-time access to updated medical knowledge. They can also hallucinate, meaning they make stuff up. Plus, they struggle with complex reasoning involving multiple clinical variables. TXAGENT addresses these issues by grounding its recommendations in verified, real-world evidence.
So it's like the difference between reading a textbook and actually talking to a doctor who's seen it all. Makes sense. How does TXAGENT compare to other AI models out there?
That's the impressive part. In their tests, TXAGENT outperformed leading LLMs, tool use models, and reasoning agents across 5 new benchmarks. It achieved 92.1% accuracy in open-ended drug reasoning tasks, surpassing even GP4O by a significant margin. It's also really good at generalizing across different drug name variations, brand names, generic names, descriptions, which is a common weakness in other models.
Wow, that's a big jump in accuracy. So it's not just better at finding the right information, it's also better at understanding the nuances of drug names and descriptions. What are these benchmarks you mentioned?
They're called Drug PC, Brand PC, Generic PC, Description PC, and Treatment PC. They're designed to comprehensively assess drug selection, treatment personalization, and reasoning robustness across structured and unstructured queries. Basically, they test how well the AI can handle different types of drug-related questions and scenarios.
Got it? So it's not just about knowing the drugs, it's about knowing how to use them in real-world situations. What about personalized medicine? How does TXAGENT handle that?
That's a key strength. TXAGENT tailors treatment strategies to individual patient characteristics, including age, genetic factors, and disease progression. It identifies contraindications based on patient comorbidities and concurrent medications. In personalized treatment scenarios, it outperformed GPT-4o and other models by a significant margin.
So it's taking into account the whole patient, not just the disease. That's crucial for avoiding adverse events and improving therapeutic decision-making. How does it actually do that personalization?
It uses those 211 tools to retrieve and synthesize evidence from multiple biomedical sources. It assesses interactions between drugs and patient conditions and refines treatment recommendations through that iterative reasoning process we talked about. It's constantly checking and rechecking to make sure the treatment plan is the best fit for that specific patient.
Okay, so it's not just a database lookup, it's a dynamic, adaptive system. What's the tool universe they keep mentioning?
The tool universe is the collection of those 211 biomedical tools. It's a generalizable toolbox that supports real-time retrieval of knowledge from verified data sources. It's built on APIs from trusted sources like OpenFDA, OpenTargets, and the Monarch Initiative.
So it's a curated collection of resources that TXAGENT can tap into. How did they even build this tool universe? It sounds like a massive undertaking.
They used a system called ToolGen, which is a multi-agent tool construction system. It automatically generates tools from API documentation. It's a 4-stage process: capability summarization, tool generation, tool validation, and human verification. This ensures that the tools are accurate, reliable, and easy for TXAGENT to use.
So it's a combination of AI and human expertise. That makes sense. What about the training data? How did they teach TXAGENT to reason and use these tools?
They created a dataset called SAGENT Instruct, which contains over 378,000 instruction tuning samples. It's derived from multi-step reasoning traces and encompasses a huge number of reasoning steps and function calls. They used multi-agent systems called QuestionGen and TraceGen to generate diverse therapeutic queries and stepwise reasoning traces.
Okay, so they didn't just throw a bunch of data at it. They carefully crafted a dataset that would teach it how to think like a doctor. What are some examples of how TXAGENT reasons through a complex case?
The paper gives some great examples. One involves a pediatric patient with Duchenne muscular dystrophy who can't take steroid treatments. TXAGENT identifies Duvizat as a suitable non-steroidal, non-exon skipping treatment and verifies its pediatric safety. Another example involves a patient taking Prozac who needs a treatment for WHIM syndrome. TXAGENT identifies that Solremdi is contraindicated with Prozac due to drug-drug interactions.
So it's able to navigate complex medical histories and identify potential problems that a human doctor might miss. That's pretty powerful. What are the limitations of TXAGENT?
The authors acknowledge that it relies on tool calls for external information, so gaps in the tool universe can limit its ability to address certain questions. Also, quantifying uncertainty in TXAGENT's internal knowledge is still a challenge, and currently it only supports natural language inputs. It can't process other modalities like images or lab results.
Okay, so it's not a perfect solution, but it's a significant step forward. It sounds like the future of medicine could involve AI agents like TXAGENT assisting doctors in making more informed and personalized treatment decisions.
So, we're diving into some fascinating research on predicting how nanoparticles behave in the body. It's all about improving drug delivery, right?
Exactly. Nanoparticles are these tiny particles used to deliver drugs directly to specific cells or tissues. Think of it as a guided missile for medicine. But the problem is, it's hard to predict where they'll go and how they'll be processed by the body. That's pharmacokinetics.
Okay, so what's the big challenge here? Why can't we just track them?
Well, it's super complex. There are so many biological interactions happening, and getting good experimental data is tough. Existing AI models try to predict this, but they often miss crucial information about the nanoparticles themselves, like their size and charge, and how those properties affect where they end up in the body.
Ah, so it's like trying to predict the weather without knowing the temperature or wind speed. Makes sense. So what's new in this research?
These researchers have developed a multi-view deep learning framework. It's like giving the AI model multiple perspectives. They're feeding it information about the nanoparticle's properties, size, charge, shape, and using something called a cross-attention mechanism to help the model focus on the most important features.
Cross-attention. Sounds fancy. What does that actually do?
Think of it as a spotlight. It helps the model figure out which nanoparticle properties are most relevant for predicting where the particles will end up in the body. For example, the model might learn that size is really important for predicting uptake in the spleen, while charge is more important for the liver.
Got it. So it's not just throwing data at the problem, it's actually incorporating knowledge about how nanoparticles work. What else are they doing to improve the predictions?
They're using ensemble learning. This means they're combining their deep learning model with other machine learning models, like XGBoost and Random Forest. It's like having a team of experts, each with their own strengths, working together to make a prediction.
So it's a more robust approach. What exactly are they trying to predict about the nanoparticle's journey?
They're focusing on 4 key pharmacokinetic parameters. These are things like the maximum uptake rate constant, how quickly the nanoparticles are absorbed, the Hill coefficient, which describes the cooperativity of the uptake, the time it takes to reach half of the maximum uptake, and the release rate constant, how quickly the nanoparticles are released from tumor cells.
Okay, so they're trying to get a complete picture of how the nanoparticles are interacting with the body. What's the ultimate goal here?
The big picture is precision nanomedicine. They want to use AI to design better nanoparticles for drug delivery, optimize how they're formulated, and ultimately make treatments more effective and personalized.
That sounds amazing. So how did they test their model?
They used a publicly available dataset of nanoparticle behavior in mice. It included information about the nanoparticles' properties and how they behaved in the body. They split the data into training, validation, and test sets to evaluate how well their model could predict nanoparticle behavior on unseen data.
And how did their model perform compared to existing methods?
They found that their multi-view AI framework outperformed other models, including standard deep learning architectures and traditional machine learning methods. The key was incorporating prior knowledge about nanoparticle properties and using the cross-attention mechanism to focus on the most important features.
So the spotlight really made a difference. Did they try to figure out which features were most important for the model's predictions?
Yes, they used something called saliency gradient graphs to visualize which features had the biggest impact on the model's predictions. They found that nanoparticle size was a major factor across the board, except for predicting the time to reach half maximum uptake. Shape, cancer type, and the engineered features also played significant roles.
That's really cool. It's not just a black box. They can actually see what the model is paying attention to. Did they do any experiments to see how important each part of their model was?
They did an ablation study. This means they tested different versions of their model, each with certain components removed. They found that incorporating prior knowledge and engineered features significantly improved performance. The ensemble learning approach also helped to make the model more robust.
So it's like they built a really solid foundation with the prior knowledge and then added extra layers of robustness with the ensemble learning. What are the implications of this research?
This AI-driven approach could really speed up the process of designing and formulating nanoparticles for drug delivery. By identifying the key properties that influence how nanoparticles behave in the body, researchers can refine their formulations to achieve targeted delivery and minimize side effects. It could also reduce the need for extensive animal testing by allowing researchers to focus on the most promising candidates.
That's a huge win. So what's next for this research?
The researchers want to expand the dataset, incorporate more types of data, and validate their model across different nanoparticle formulations. The goal is to make it even more accurate and applicable to a wider range of clinical scenarios.
This is a really exciting step forward for precision nanomedicine. It's amazing to see how AI can be used to tackle such complex challenges and potentially revolutionize drug delivery. Wow, what a journey. From extensions that help us navigate the tricky world of online information to AI that's revolutionizing medicine, it's clear how rapidly things are evolving.
Absolutely. I'm still thinking about how AI can help us become more critical thinkers online. The idea of having an AI sidekick to point out logical fallacies is pretty wild and definitely needed these days.
And the potential for AI to design personalized medicine is just mind-blowing. Imagine a future where treatments are tailored to your specific needs based on your unique genetic makeup and medical history. It feels like we're on the cusp of a new era in healthcare.
It's not just about medicine either. The way AI is learning to generate realistic 3D environments by pulling information from multiple sources is incredible. It's like giving AI a sense of creativity and spatial reasoning.
And let's not forget about making these algorithms learn faster and more efficiently. That work on optimization is crucial for unlocking the full potential of AI across all fields.
Definitely. And the way AI is being used to evaluate math problems, not just the answers but the entire problem-solving process, is a game-changer for education. It's about understanding how AI thinks, not just what it produces.
It's all about augmenting human capabilities, not replacing them. Whether it's helping us spot misinformation, design better drugs, or learn more effectively, AI has the potential to make a real difference in our lives.
I'm excited to see where all this research leads us. There are still challenges to overcome, but the progress we're making is truly remarkable. Who knows what we'll be discussing on the next episode?
Exactly. The possibilities feel endless. Thanks for tuning in, and we'll catch you next time for more AI by AI.